Okay, here we are for Chapter 2, Functions. I hope the first test went well for all of you last week. I'll be grading that this weekend, so we'll see how you did. A little introduction to functions. A quote from the book says, one of the most useful mathematical ideas for modeling is the concept of a function. And I think you all remember that functions are indicated usually with that notation which reads f of x. It's not always the f function. Sometimes you have other functions in there as well. But just a general rule here. If a rock climber, or a general example I have, if a rock climber drops a stone from a cliff, what happens to the stone? And in general terms, you can say the stone falls. Okay? More specifically, you can say, and it hits the ground. Okay? Even more specifically, in terms of a function, or more specifically, you could say in t seconds, something like this, the stone falls 16 t squared feet, as this function indicates. This we read as d of t. The distance at a specific time is the same thing, the distance at t seconds. Of course, these variables have been identified earlier as well. Distance at t seconds, etc. Okay. Now, you can also, functions can also be indicated by tables, by graphs, if you're more visual. When we plug in this function into our calculator, which I'm not going to do, I did it ahead of time, and adjusted my window over here, you can see my graph. I scaled it on the x-axis for seconds, for 5 seconds, and the y-axis for feet. Okay? And after, you can visually read this after 3 seconds. How far has the stone fallen? If you have a table function in your calculator, it has fallen 144 feet over here. And if by plotting the points, you would get this curve. Okay, so in terms of what a function is, we can represent functions, mathematically by equations, but we can also describe things by functions and visualize things using graphs and tables and whatever works for you. Okay? Now, more technically, a function is a rule, and we usually use, f of x, g of x, h of x, to represent these functions. Now, x, this is the important part, the x is what's called the input, or sometimes the domain of the function. Sometimes that domain is restricted. It's also known as the independent variable. Whoops. Let me get this thing off the screen here. Move this up here. The independent variable. Okay. Now, usually what you have considered as y now becomes our f of x, okay? Y is the output, or sometimes better known as, if we don't have domain, we've got our range, okay? And therefore making it the dependent variable. Okay, y depends on what's happening with x. Some other examples of function, just everyday functions. You could say that height, your height, could be a function of your age. And if that's the case, just try to indicate, especially when we're doing these modeling problems, make the variables stand for something. So your height could be a function of age. You know, temperature could be a function of the date. Temperature as a function of the date or time of year. You know, time of year. Now try to avoid using the same letters. So this one we might say T of D, function of date. We've got a lot of geometry formulas that are functions. Okay. How about area of a circle? Now you're used to hearing area of a circle is pi r squared. So the area of the circle is a function of the radius. Okay? Function is based on the radius. So pi times radius squared. Dependent variable, independent variable, okay, in that situation. All right, now to evaluate functions, I'm sure we are okay with something like this. If we have f of x equals 2x squared minus 5x, hopefully you did this back freshman year in Algebra 2, but instead of saying, you know, y equals 2x squared minus 5x, find y when x is 3, we just use our shortcut now and say evaluate the function at 3, f of 3. So that means we replace all of our, everywhere where we see an x, we're going to now fill in 3. Okay? And square the function at 3, and then subtract it by 5 times. I'm sorry, not square the function. We do 2 times 3 squared minus 5 times 3. So if we're evaluating that a little bit further, we've got 9 times 2 or 18 minus 15. That happens to be 3 again. But f of 3 would equal 3. Okay? How about f of, if we have negative 3, that one. That would give us, again, 18, but this time it would give us plus 15. And f of negative 3 would end up being 33. Okay? Now we're going to use a little bit more complicated evaluations. We can do that on the calculator. Remember last week I showed you how to plug in functions and then go into the table to look for them. So that's easy enough to do. But what if you can't do that on the calculator and I want you to evaluate something like f of, come over here and do this, say something like f of a plus 1. That means everywhere where you see an x, again in the function, we're going to replace that this time with a plus 1. So let's just do this. Use parentheses when you're substituting. Okay? And then we can simplify. Don't forget to simplify. All right? A plus 1, that quantity squared, becomes a squared plus 2a plus 1. We can distribute the negative 5a minus 5. Distribute the 2. And then get your like terms together from there. So 2a squared minus a minus 3 for that one. So as you can see, you're not just plugging values in, sometimes you're plugging in other expressions. Now, one of the more common functions that we know of in calculus is something called the difference quotient, and you're going to learn this next year to evaluate limits. Actually, we're going to do this at the end of this year, so it's worth taking a look at. And the difference quotient states that f of x plus h usually stands for a horizontal shift. It will make more sense when I explain it in terms of graphs and what we're doing here. We're really just finding slope. This stands for, has something to do with slope. I do have to stipulate that h cannot be 0 because then we would not have a function. So let's take the function we just looked at. Let me just write it down here where I can see it. F of x equals the 2x squared minus 5x. And I'm going to now substitute that into the difference function. So if I have this function, I want to, I'll say something like this. If the function equals that, then evaluate this, f of x plus h minus f of x divided by h. And here's what you do for this. Follow these steps here because this can get a little bit confusing sometimes. Again, I'm going to do my f of x plus h first. So I'm going to take x plus h, I'll do this separately in colors, and substitute in x plus h wherever we have an x in our original function. So that's after the 2, and we're squaring that, and then also after the 5. I'm going to plug in x plus h there. Okay? Then we're going to subtract the original function. So I'm going to subtract, and I'm going to please put this in parentheses as well, the 2x squared minus 5x. And then all of that is going to be over h. So as you can see, you need to do a bit of simplifying here. Okay? Take your time with this. I'm going to expand x plus h squared. That becomes x squared plus 2xh plus h squared. Distribute the 5 minus 5x minus 5h. Distribute the negative sign to the function. This becomes plus 5x. And again, everything is all over h. Okay? After we distribute through with the 2 up top, several terms should cancel out if we did this accurately. I'm not going to rewrite the denominator right now. Okay? Let's just simplify my numerator. So what is going to cancel out here? The 2x squares cancel, and negative 5x and 5x cancels. So now we're end up with 4xh plus 2h squared minus 5h all over h. Now what do all of those terms have in common? An h. So we're going to factor out the h up top. Let's do it accurately by factoring. And we're left with 4x plus 2h minus 5 divided by this h, and then my h's cancel out. So my final solution here, if I'm evaluating this function for the difference quotient, would be 4x plus 2h minus 5. We take it a step further later on in the year with the limits, and this will be something that has to do with differentiating or taking the derivative. Okay? So play that back again if you got lost in there somewhere. That was one of the harder problems where we have to evaluate that difference quotient, but try that again. Okay, the last thing I'm going to cover in this first video is domain, and we talked a little bit about that last week. Let me just scroll through here. Okay, the domain, first of all, we need to know what that is. That's your input or your x value. So it's all values for x, all possible x values or input values. Let me write it that way. Okay. So you just need to become familiar with some of these functions, and once you do and can visualize what they are, then writing their domains is simple. My first example is a quadratic, f of x equals 3x squared. What you should try to do is think of, are there any limitations to the input? What can't x be? I think sometimes that would help. So for this first example, 3x squared is a problem. Again, there are no restrictions on the domain, so your domain is all real numbers. I'll stick with that interval notation, or if you just want to write, the symbol for all reals, that's fine as well. Okay. The second one, what can't x equal? X cannot equal 4. If we have 4 in the denominator, that gives us 0 in the denominator. Okay. Again, if we're writing that in interval notation, we have negative infinity to 4 or 4 to infinity. Okay. You can just say it's all reals except x cannot equal 4 if you want. And then the last example, getting close to my cutoff time here for my 15 minutes, we've got the square root of x plus 2. What do you know